that, she is a university graduate fellow. She is studying to get her PhD, along with being staff as well. So staff and student at the same time. Her research is about Mars, and because she works with HiRISE, she's going to tell you about her work today, and you get to see her work in 3D. So I guess let's go ahead and get started. Take it away, Sarah. Thanks.
Thanks, Sarah. So many Sarahs. Okay, so first of all, can everybody hear me? Can anybody hear me?
Speak right into it.
Can anybody hear me? Yes. Okay, you don't need your 3D glasses yet. Sorry. Okay, so first of all, thank you for the introduction, Sarah. That was really nice. You saved me like 2 slides and a lot of background. So I want to know who wants to go to Mars. Okay. Who thinks they're ever actually going to be able to go to Mars? Yeah. All right. Well, so what I'm going to show you is the closest you may be able to get to Mars, and it's free, and it's easy, and it's really nice. So I'm going to talk about the image on the slide really quickly, which is an example of what I'm discussing, is that this is an image of Mars. And what I've taken is a perspective view of a real place on Mars as if you were there standing looking at these dunes. And there's dunes and rocks and things that you can recognize because we see them here on Earth. So it's all about getting the human perspective of maybe traveling to Mars. Okay, Mars. I'm not going to talk a lot about what Mars is, except that what the most important features to us is an active world. It's got a lot of geology on it that we care about as geologists, and I don't want to hear anyone say that it's a dead planet. It is not. It's a very busy place. So, back to Mars. We have canyons. The biggest canyon in the new solar system is the Valles Marineris. We have volcanoes. The largest volcanoes in the solar system are on Mars. Polar caps. It has icy processes. Can everybody still hear me? Yes. Okay, it's changing. There's an atmosphere, so there's weather. Weather makes things happen. And there's climate, because the obliquity of Mars changes. It actually tilts more and less over tens of thousands of years. So you get these really drastic climate changes that are different than weather changes that we experience. All right, so a little bit of background about HiRISE. It's the High Resolution Imaging Science Experiment. And high resolution is the only part you have to remember, and what we mean by that. So I'm going to give you a few basics into the camera. So here's Mars. Here's the Mars Reconnaissance Orbiter, and that black thing sticking down that looks like a peg. That's HiRISE. It's the solar. It's the baffle around the telescope. It's a 0.5 meter diameter telescope pointed at the surface of Mars. So it's actually a gigantic instrument to fly on a spacecraft. It's a very complicated instrument. I'm not going to go into all the details of how it works, because that would take a long time. But the important thing to know here is that it's pixel scale. So we all know what a pixel is in our pictures now that are digital. 1 pixel of a HiRISE image is about 30 centimeters, which is about a foot. So we can image very high detail things on the surface of Mars. We have a lot of pixels in our images, like a gigapixel, but it images a very small piece of the surface. So what's the most important thing to remember about HiRISE? Yes. This could be important later. Okay. So here's a few numbers about the HiRISE camera besides the important part about resolution. As of a few days ago, we have acquired 47,239 observations while we've been in orbit for 10 years, and we're still going strong, so there will be thousands more, we hope. However, we've imaged less than 3% of the surface of Mars if every one of those observations was unique coverage on Mars. Also an important fact to keep in mind. So no, we're not going to map the entire surface of Mars in, at 1 foot resolution. This is not going to happen, no matter how long the mission lasts. But we also do this thing where we image the same piece of ground at least twice, and then maybe multiple times, and that's really what I'm going to talk to you about tonight. And another important thing is that we acquire these images called stereo pairs, which is 2 images of the same piece of ground. I'm going to give you a little more information about that. So we've acquired almost 5,000 stereo pairs of Mars, and we've made almost 5,000 anaglyphs, which is what you need those red and blue glasses for. That's a 3D image, which we are not looking at yet. And then we've made only about 335 of these into high-resolution topography models, or digital topography models, or DTMs. And why so few? Well, it's actually really hard to make those, and I'll tell you a little bit about that. And there's some people here that will help you. One really special thing about HiRISE is this data release policy. Wow, that sounds so exciting, data release policy. But what's really neat about it is HiRISE has been called the people's camera ever since it started. And our PI, Alfred McEwen, has a policy that there is so much wealth in the data returned from HiRISE. It will provide enough information for scientists to use for careers, lifetimes of careers, and we don't need to hold it back. We need to get it out to the community as soon as possible. So we release our data ahead of the NASA required schedule. We release it every month as soon as it's validated, and we give it to you. It's out there in the public for you to enjoy. And we also release DTMs monthly out there available. Okay, there's our website, uahirise.org. Fun place to go, especially if you have those full 3D glasses. And HiRISE is a tool on our website where you can actually enter a target that you would like HiRISE to take an image of the surface of Mars. And what's neat about this is anyone can do this, anyone can use this tool, and all the team members use this tool because it's so easy and it's like, so you're doing the same thing we are doing. We target images of Mars with HiRISE. And what's really fun is after you get your image acquired, you get an email that says, hey, your image is acquired in Mars, and you can see it online, and you can tell your mom. This will be really impressed. And HiRISE images, as I mentioned, are humongous. They're like really hard to just look at on your phone or your laptop or whatever, because you don't want to download them, gigabyte image, and it's just, so we have this other cool tool called HiView that basically streams over parts of the images because they're in a special format, and you can look at them without having to download, terabytes of data. So HiView is also a free tool that's available. It's really fun. Okay, stereo imaging. Briefly, we image in stereo with our eyes all the time. We try to reproduce this with the spacecraft. We fly MRO in one orbit, and we image something on the ground. We have to come around on another orbit, which will bring us optimally close to that same target, but from a different angle. And we try to reproduce the same kind of angle that we have between our eyes to perceive depth. And that's what stereo imaging means. So we get 2 separate images taken at 2 separate times. We have to combine them to then be able to see depth. How does this happen? Well, we have an automated pipeline that generates the anaglyphs that you can look at with those red blue glasses. And for the DTMs, I have a small army of undergraduate students who are super talented. And I know some of you are here tonight, and I want you to stand up and wave because you are awesome. Yay! And I can't tell you how great these students are, and they're going to be, amazing contributors to the community. They've already contributed so much to what we do. And I just want you to know that there are people toiling in computer sweatshops to produce data for you. Okay, so here's a stereo image, a stereo pair, we say. And you're like, stereo pair, well, that just looks like 2 pictures of the same thing, but they're slightly different. And when you look at that in the red blue glasses, you can now perceive depth. So what this gives you is a qualitative look at the image. You can tell what's higher, what's lower. You can get a sense for, how steep something is. You can't make measurements on this, but you can certainly get a feel for how the terrain is. So these are really great to look at, and there are thousands. How many? Almost 5,000. How many? on the website. You can look at them. You can waste a lot of time looking at these online. They're really fun. So why is stereo imaging so important? Why am I here telling you why this is so great? Because I think it's great, but maybe you don't care. So why it's important is that topography gives us information that you don't see when you're looking at these images on the left. Like, you don't really understand what you're looking at. It just looks like some stuff on the ground. So here, this image you're looking at, the rainbow colored one on top is the topography map, where blue is lower elevation and red is higher elevation. The bottom image is the actual image of the surface. And you can see the information in both those images is not really correlated very well. You wouldn't be able to interpret what's happening, like where is their drainage channels, where are their canyons, where are their hills, just by looking at the image of the surface. So this is really important information, and it takes a lot of work, a lot of planning, and a lot of work to get this information out of these images. It's super valuable. Why is it valuable? It's valuable for science, for one thing. So we can do geology on other planets with this type of information. And I guarantee you that any science release that you've seen about planets in recent times, about Pluto, about Mars, about the moon, I'm 100% sure that almost all of those press releases have a topography map included in some way. You may not have noticed it, but I did. And I was very happy because it's all about topography. And that's something I want you to remember. And so another reason stereo information is really important is visualization. We can visualize the surface of other worlds without having to go there ourselves. And that's important for planning and understanding the science. It's also important for connecting as human beings to another place. Public involvement. This helps us explain things about Mars to people that maybe aren't planetary scientists in a way that we can relate to, because we know we can see Earth, and Earth is a planet. So we can relate other places when it's shown in a perspective that we are familiar with here. And it's fun. So remember, it's all about topography. Okay, so let's talk about science. So as I mentioned earlier, Mars is a very active planet. There's a lot of activity on the surface. And I could have a whole talk about just that, and I've done that, and it would go on and on. But I'll just summarize some of the active processes that we've discovered with HiRISE that we couldn't resolve earlier than this mission, but we guessed might be happening, like active dunes. RSL, what's that? That's a recurring slope lineae, which is a very unsexy name for a very interesting process on Mars, where there may be liquid water activity on the present surface of Mars, which is not supposed to be possible. Like, okay? Okay. That was something that was discovered with stereo data. Gullies. Gullies on Mars are like ravines on Earth. And this picture is of a dune. That's actually a gigantic dune. It's a mega dune. It's 400 meters high, which is really hard to comprehend. Those lines on it are called linear gullies, and like, what makes those happen? So that's a research topic, and we can watch those change on the surface from year to year. There's polar processes. We have, like I said, seasons on Mars. We have frost coming and going. Impact craters, that's happening all the time, and much more. So dunes, active dunes. This should start to go. So, okay, I can't see that. All right, so this is one of the first things that we're able to do with the TTM. You have high resolution topography. You take image after image after image of the same place on the surface, and then you can reproject those images to exactly match the topography, which is called orthorectification. Tip, orthorectification. Ortho images, really important. Because you notice that things are changing in the image, but not everything is changing. So the ground between the dunes is not moving. And the dune surfaces, those ripples, those are actually mega ripples, because even though Mars is about the fifth of the size of Earth, all the surface features on Mars seem to be 4 times bigger than anything you find on Earth. Those are mega ripples, and they're moving. The little clock dials on the right, each one of those dials is a year at Mars, and so the red line shows through the season where that image was taken. Lots of details. Just notice that the ripples are moving, and this is something that allowed us to start to constrain that there's dune activity, and this is, we have wind that moves sand. Believe it or not, this is super exciting. Because when someone says, oh, that's a dead planet, it's geologically frozen, nothing's happening, that's not true. It's happening all the time. So, to show you how much sand is moving on Mars, this is a very cool sequence. This is 2 images taken 5 Mars years apart, because that's how long we've been at Mars. Mars years about 26 months or 2 Earth years. Check that out. Those dunes are moving a lot. Look at the scale bar. That scale bar is 100 meters. That's 100 yards. That's a football field. Oh, sorry. Back. So the ground between the dunes is not moving. Sorry. Those are moving a lot. Cool. Recurring slope lineae, the very exciting thing that I told you about earlier with the terrible name. This is something that this is a crater in the floor of Valles Marineris, which is in the equatorial region of Mars. It's a canyon bigger than the Grand Canyon. It spans almost the whole width of the United States. So you'll see, is it moving? You'll see these streaks, and they follow the direction of the sun, indicated by that little yellow sun thing. And you'll see them change. What happens is they appear, they slide downhill, they fade. And this all happens within a season. So what's happening with it? What's making this happen? That's a big research topic. It's spawning lots of meetings, lots of papers. And that was discovered here at the U of A in HiRISE operations in my lab by an undergraduate student. So really cool things happen, and it leads to really new science. Because if there's liquid water existing on Mars right now, currently, that has implications for astrobiology, for habitable environments, for human exploration, and all kinds of things. If it's not liquid water, we need to understand what else is happening. Gullies. Gullies are cool. And there's a lot of them on Mars, and there's a lot of controversy about what forms them. They look like they would be formed like by rain, like they are here on Earth, where rain falls down hills, it erodes, and it carves these deep grooves. But there's no rain on Mars, and there hasn't been for a long time, if there ever was. So how are they being formed? Lots of science fights about this. But we can watch them form today, and we know that a lot of them have to do with carbon dioxide ice, dry ice activity on Mars. Carbon dioxide is either frozen or gas on Mars. It's never in liquid form, and so it's causing material to fall downhill. And that's an active process that does not exist on Earth. Here's another kind of bizarre image, like, oh, what is that? That looks like bacteria or mold or something. This is carbon dioxide frost in the southern polar region of Mars, in a really cool, weird, bizarre area called Inca City. I think that's an unofficial name. Yeah, so over seasons, this part of the ground gets covered with like a couple meters of carbon dioxide ice that accumulates and then cracks, and these jets blow sand out on top of them, and then they sublimate away. And this is a seasonal process, and understanding this is pretty difficult because this doesn't exist on Earth. So we have to figure it out from images and spectra. Another really neat polar process, here's a DTM of the North Polar layer deposits of Mars. That's kind of like a polar cap, but it's not really a polar cap. And so these are layer deposits that are considered pretty recent. So recent climate of Mars, like hundreds of thousands of years maybe. So we want to understand how the climate of Mars is evolving. And this is a very large cliff. And we're able to get a perspective of this through these 3D views, where we can actually get a feel for how steep is this cliff, and what do these layers look like, and how they germinate. Impact craters, lots and lots of impact craters. You know, I'm kind of like, oh my god, not another impact crater. But actually, this is also another really important process, because these impacts excavate the subsurface of Mars. So we can actually understand the geologic strata of Mars by impact craters, which then lift that material out and allow us to see it. this is a really cool impact crater, so it's kind of a montage of a crater. Well, is it an impact crater at all? That was the question. It's a little hole in the side of a really big volcano with no other features around it. So you can see through this hole to the pile of debris about 30 meters below the hole. And so I made a DTM of this, and we did all kinds of measurements of the slope of the sides and how much mass fell through to the hole, like how much stuff that's in the bottom, like how big is the cave? It's a big cave, big enough for astronauts to go into. I don't know. Oh my gosh, here comes the train. Okay. Visualization. So I talked a lot about geology already. And how many of you have heard of Curiosity? Good. Curiosity, the Mars Science Laboratory, MSL. That is on Mars right now in this really neat crater called Gale Crater. And mission planning it was impossible to plan, and it's impossible to plan for any robotic spacecraft to explore Mars without DTMs, without high-resolution topography. This picture is a colorized elevation map of the landing site where MSL landed, or Curiosity landed, or part of the landing ellipse, I'm not sure. Actually, I think it's just part of the landing ellipse because the actual landing site is very flat and very boring, and I would never show you a picture like that. But these are actually dunes, and they're part of a very now famous area of dunes called the Bagnall Dunes that the rover has actually traversed. And it's the first close-up look of really substantial dunes on Mars that we've seen, and they're pretty stunning. So landing site assessment and mission planning cannot happen without this high-resolution topography. Because why? Topography is everything. Okay, so here's a really cool animation of where MSL is at Gale Crater. And why I want to show this to you is because we can go where the rover cannot. So we can look at the same topography, but we can explore places that are inaccessible to the rover. And this is one way to do it. And I want to say, Nick, where are you? Nick, stand up, wave, take a bow. Nick made this beautiful animation like yesterday. So we'll have more of these coming. Yeah, could watch that all day. So visualization, what am I talking about? You look at this, I look at pictures like this all day long, so I'm really comfortable with this view. And maybe now that we have Google Earth and Google Maps, we're more comfortable with looking at these images. We're like, oh yeah, satellite images. I get that. But really, it's actually really hard to understand what we're seeing from this perspective. So visualization with 3D gives us a better perspective. Is it choo-choo time? Okay. Okay, so this crater is 14 kilometers in diameter. Who knows what that means, really? You could fit about half of Tucson in this crater. That's really big. Like, where is your neighborhood? Where would it be? In the pit? Here's another beautiful animation by Nick. So we're going to fly over the rim of this crater, and we're going to go take a little tour. And you're going to get a whole different view and a different feel. Just remember, just imagine you're flying over half of Tucson while you're doing this. It's awesome. It's almost like being there, right? Too much? And you can see the slump down, and there's gullies, and there's a pit in the middle, and there's mountains and rocks, and it's a crater, an impact crater sciences crater. It's a really nice crater. Beautiful. Thank you, Nick. That was great. So what else? Fun. This is fun, right? I'm having fun. Who has seen The Martian? I haven't. I know. I'm too busy. Okay, so there's a funny story about The Martian and HiRISE. They didn't actually use any of our terrain models in their movie. I don't know why. But they didn't. But it looks beautiful anyway. But we got this call or an email from the author of The Martian. He emailed us and he said, you know, you have an image that's pretty close to where Mark Watney landed, but not really. So could you maybe like take another one? And we did. And he's like, well, while we're at it, we'll take stereo care. And while we're at it, we'll make some DTMs. And my students made DTMs like that. And, you know, it went all the way up NASA. It was pretty exciting. So actually, it turns out that this site, this is the Ares 3 landing site of The Martian, not a real Mars mission, but a fictional one. It's actually pretty interesting. These craters are really weird, and if anyone can figure out what explains their morphology, you know, you've got a science paper. Another thing, there's this really neat game being developed called Lacuna Passage. They're using our HiRISE DTMs. In fact, we corresponded on Twitter, and if you look at their blog, their development blog, which is incredible and really neat if you know about game development, their very first blog entry is about using HiRISE DTMs. And then as they've updated, I can't wait for this game to come out, although I won't have time to play it because I'm too busy. But it looks really beautiful, and there is HiRISE topography model, so it's like really going to be at Mars. And the other thing that's fun is you. You all are here tonight. I take it that means you're kind of interested, or maybe you're just here for exoplanets. I don't know. But I want you to know that you can have these data. We make them for you, and you can. They're free. You can download them. You can do your own thing. This beautiful movie was made by someone who just grabbed one of our DTMs off the website, wrote software for virtual reality, and now has this amazing site called Mars3D.com. And if you go there, you can get stuff for, I don't know, Oculus Rift and fun things that people have time to play with fun things and explore Mars in virtual reality. So that's really great, and it makes me really happy. And it makes me really happy when the public contacts us and says, well, I really like your DTMs, I want to use them, or like, go for it. Okay, now you can put your 3D glasses on again. This is a really interesting fracture, and it's in 3D. So I want to remind you that you can go to our websites, uahirise.org, DTM, get the DTMs, you can go to the anaglyph site, you can look at anaglyphs, there are thousands of them, and they're really beautiful to look at and fun. And you can go enter your targets on HiRISE. So thank you Borderlands, thank you Spacecraft people, and thanks to the HiRISE team, and thanks to my students too. I can take questions, or I can ask a trivia question, because we have prizes. Okay, question?
Yeah, you talked about the importance of topography a lot.
Yeah.
Do you like surface integrals?
The question is, since I love topography so much, do I like surface integrals? The answer is yes, because I'm a math major and I love math, and surface integrals are very mathy, so yes. Yay, math. Math is awesome too, but that's a different talk. Good job. Question is that?
What's the eventual goal? Complete the path at Mars, with some coordination, or use for this one for lifespan? What's the eventual outcome that you wish?
Okay, the question is, what's the eventual goal for mapping Mars in global, I assume higher and higher resolution is what you're kind of after? Yeah, that's a great question. Obviously, HiRISE is not the instrument to do that. We take pictures of only the most interesting 2% of Mars. The rest of Mars is also interesting, but we're not. So there's another camera on on Mars Reconnaissance Orbiter called the Context camera. It has a much larger field of view, slightly lower resolution, 6 meters per pixel, which is still incredible. And I think at this time, CTX is the name of the Context camera, CTX. I think they've imaged almost the entire surface of Mars, maybe some places multiple times. So they're able to actually build up a very high resolution global image map of Mars. So there's that. The Europeans have a spacecraft that has just arrived at Mars called the Trace Gas Orbiter. There's a camera on that mission that is called CASIS. It's a color and stereo science. Sorry, I should know that because I'm on the scene. But they are sort of between HiRISE and CTX in terms of resolution and image size. Now, I don't think their plan is to globally map Mars, but we can only hope. So that would be a nice in between, and they also have a very strong stereo imaging emphasis in their mission. Does that answer your question? It's happening. Question?
So you mentioned how the stereo imaging can be used to determine depth and height. Can it be used to determine depth of solid like ice?
So we only can image the surface, but other instruments like radar can penetrate the surface. And there's another instrument on MRO called HiRISE, which is shallow radar, although actually it can image quite deep, and it has actually seen through the whole North Polar Layer deposits. And there's an amazing amount of work that's been done to build up a 3D map of those deposits with radar. So radar is the way to see through to depths of ice and subsurface changes. Not cameras, unfortunately, but you know, we need to have other people do other kinds of science so we can all collaborate and bring all the whole picture together.
I got a question.
Problem.
Is HiRISE secretly a spy camera because it was like a whole gigapixel back in 2006 and that was pretty damn huge?
It's HiRISE spy camera. We're spying on Mars. Yeah. I don't know what spy cameras are like on Earth, but I think that HiRISE is the highest resolution camera ever flown to another planet, for sure. To date, still. But I'm sure we won't hold that title forever. Trivia question? Okay, here's one trivia question. Or do you have trivia questions? Okay.
So the trivia questions are to test that you were paying attention during the talk, but the prizes are fun.
Yeah. So I have a trivia question about my talk, and you get a prize if you get it right.
What's the prize?
Cool Mars posters.
Travel poster for Mars.
A travel poster of Mars. That's pretty good. About what percentage of all the stereo pairs have been released as DTMs to the public? Tricky question. Tough one. My students may not answer this question. Shout out.
300 and
Percent? Or number? Or number?
But you got the number right, so just divide it to
10%. He wins. Okay. Anything else? All right. Thank you guys so much for your time. Really enjoyed it.
We're going to take a couple minute intermission.